Awesome. So let me share my screen. Yeah, so hey everyone, thanks for joining Multimodal Weekly. This is a virtual webinar series hosted by 12 Labs. For those of you who are new to a company, we're in a Series A startup focused on building multimodals, video studying models. And this is a community initiatives that we've been working on over the past almost 2 years or so. We've been meeting on a weekly basis, and we discuss a variety of topics. Obviously, a big chunk of that is focused on the research side of things, inviting researchers coming to talk about multimodal AI foundation models. Oftentimes we have, people from our communities. So think about like developers, startup founders, creators who talk about, and partners as well, who talk about innovative multimodal application in different verticals, projects that build. Oftentimes we have internal team members come talk about how to use our platform and API. Here's a sample of some of the recent session that we got. Big chunk of that is the researcher side of thing, right? We have people talk about like, let's say the evaluation side, multimodal models, to working on video question answering, working on like the processing side of things. And last week we had like a partner talk where some of our partners come talk about how to use our tools to do auto highlight generation for specific use case in sports. So for today's session, we'll have three presentation, all on more on the research side of things. So we start now with Zujin Guo, who's currently a research assistant at the S Lab in Nanyang Technology University, and he will present his work called GIMM, Generalizable Implicit Motion Modeling, which is a novel and effective approach to motion modeling for video frame interpolation. And then secondly, we'll have Kamran Janjua and Hossein Qasimabadi. Hopefully I got your name's pronunciation correct.
Yeah, that's good.
They both from Huawei Technologies in Canada, and they will present the work called Turtle, which is a method to learn the truncated causal history model for efficient and high-performing video restoration. And then we closed out our webinar with Mingfei Han, who's currently a PhD candidate at the University of Technology in Sydney, who will present his work called Shot to Story, a new multi-shot video understanding benchmark datasets with detailed shot-level captions, comprehensive video summaries, and question answering pairs. So yeah, you can see we have pretty exciting lineup for today's session. And just a quick note on the logistics side, after each presentation, feel free to send your question in the Zoom chat, and then we have an interactive Q&A after the speaker finish. So with that, I will stop sharing my screen. And yeah, Zujin, why don't you go ahead and get started? You can share your screen.
Yeah, okay. So can you see my screen right now?
Yep, we can see it.
Yeah, okay. So first, thanks, James, for the kind introduction. And hi, everyone. This is Zujin from S Lab at Nanyang Technological University. And today I'm thrilled to share our recent NeurIPS work on generalizable implicit motion modeling for video frame interpolation in this webinar. So to start, let's take a quick look at our approach. Given two input frames, our proposed method, GIMM-VFI, effectively models the intermediate motion and enables seamless interpolation of the intermediate frames at arbitrary time steps. So in the video frame interpolation task, flow-based methods are widely favored for their effectiveness and robustness. Before introducing our GIMM method, let's first review the fundamentals of the flow-based video frame interpolation, aka VFI. So given a pair of adjacent video frames, a typical flow-based VFI process consists of two key stages, which are motion modeling and frame interpolation, where the later frame interpolation is guided by the estimated motion from the first stage of the motion modeling. As you can see here. So in this work, we primarily focus on the motion modeling stage, which is crucial for achieving accurate interpolation, as it provides the necessary guidance for generating intermediate frames. While accurate motion modeling is crucial for frame interpolation, a common approach in previous work is to linearly combine the flows between the input frames, assuming that the motion simply overlaps. However, this assumption is often too restrictive, resulting in coarse and ambiguous motion, as shown in here, so figure A and case here. Another approach, as shown in the sub-figure B, involves time condition-based modeling without leveraging the motion priors between the input frames. However, this can result in suboptimal motion estimation, leading to inaccuracies and blurring results. So in this work, we propose a generalizable implicit motion modeling strategy, as shown in sub-figure C, and our approach effectively captures the intermediate motion by leveraging motion priors and generalizable implicit neural representation, enabling better frame interpolation. And the goal of our motion modeling module, GIM, is to estimate the intermediate motion at any time step between 0 and 1, leveraging bidirectional flows between the input frames. These bidirectional flows act as motion priors and are predicted using a pre-trained flow estimator. And here, GIM is a generalizable implicit neural representation, as I mentioned before, that employs an adaptive coordinate-based network conditioned on motion Latin and spatial temporal coordinates. And unlike non-generalizable implicit neural representations that often requires test time optimization for different input instances, GIM is free of such test time optimization with the help of the input-specific motion Latin. So now the next step is to ensure the motion Latin effectively capture motion priors. We propose a motion encoding pipeline to model the spatial temporal motion Latin from the bidirectional flows. So specifically, we begin with the bidirectional flows, aka as the motion priors. Since both the motion priors and the intermediate motion can vary in scale and direction, so we first apply flow normalization to standardize the motion representation. Next, we extract features from the normalized flows using a motion encoder, as the raw flow estimated by the pre-trained flow estimator can be noisy. And to ensure spatial temporal consistency in the modeled motion, we forward warp the features of the normalized motion towards the target time step t, and then refine them using a Latin refiner to predict the final motion Latin. Here, both the Latin refiner and the motion encoder are structured as shallow convolutional networks. And as mentioned before, this predicted instance-specific motion Latin enables our generalizable implicit motion modeling across different videos. Using this instance-specific motion Latin and the spatial temporal coordinates as input, the coordinate-based network directly predicts the intermediate normalized flows, which can then be denormalized into bilateral flows that are going to be used in the next stage of frame interpolation. So here in the first stage, the motion modeling module is trained to use a simple L2 loss, which directly supervises the predicted normalized flow. After the motion modeling module has been completed, we move on to the second stage, frame interpolation. In this stage, we backwarp the input frames using the modeled motion from previous step supplied by GIM, and then continue with the predicted warping mask to generate the final output. For the components, the choices can be quite flexible. The pre-trained flow estimator can be any method for flow estimation, such as raft and flow former, and the frame synthesis module can also be freely adapted from the frame synthesis parts of most existing flow-based VFI approaches. So for training, we optimize the GIMM-VFI using a combination of interpolation losses and reconstruction objective for the motion modeling module to preserve its motion modeling ability. And here we present visualizations of the modeled motion and the interpolated frames. Compared to other methods, GIMM-VFI generates the clearest motion and the most accurate interpolations, demonstrating its excellent performance in both motion modeling and frame interpolation. For quantitative motion modeling evaluation, we conduct experiments on both motion and interpolation benchmarks. On motion benchmarks, VTF and VSF of 2 times and 6 times motion, we calculated the PSNR on the normalized flows and EP on the denormalized flows. And for the here the SNU film arm is 8 times interpolation benchmark, and we calculated the PSNRs for the interpolated frames. And the comparisons are primarily made between the linear model and the end-to-end approach and our GMM, which refer to the strategies as outlined in the motivation section as in the previous slide. And here we mainly have 3 key observations. First, GM can continuously model motion in videos, since it is trained only on the 2 times motion dataset and can outperform other methods on the continuous motion benchmark VSF. And second, the motion priors are important in both motion modeling and the downstream interpolation task. We observe that a method with motion priors indicating the linear forward warp and the GIM outperform all the other methods on all the benchmarks. Third, other modules may impact the result of interpolation. As you can see here, the end-to-end method has a narrower performance gap compared with other advanced approaches on the interpolation benchmark here than on the motion benchmarks, likely due to it has more complex feature extraction and frame synthesis modules. And we further investigated the necessity of the usage of the implicit neural representation and how to make it, and the way how to make it generalizable. So specifically, we explore replacing the INR with UNet with a UNet as used in diffusion models, or adopting a meta-learning-based approach to predict the weights of the coordinate-based network instead of encoding a motion latent to enable INR's cross-video generalization. However, neither of these alternative outperforms GIM in terms of motion modeling or the model efficiency. Additionally, we conducted an ablation study on the GIM model to validate our design choices, including skipping the forward warping operation and removing the implicit modeling by removing the input coordinates and removing the motion encoder, removing the latent refiner, and removing the spatial coordinates from the 3D coordinates. And as shown in the table here, removing any of these components negatively affects the motion modeling performance. The effectiveness of our design choice is therefore demonstrated. And we further compare the interpolation results with other methods reporting PSNR, LPIPS, and FID scores. Our proposed method has achieved state-of-the-art performance across all the benchmarks. And here's another visualization of the interpolation, where we compare the GIMM-VFI. Here, GIMM-VFI R means the GIMM-VFI raster-based GIMM-VFI, and the GIMM-VFI-F means the flowformer-based GIMM-VFI. And as you can see, in these large motion scenarios, GIM effectively preserves the texture details and presents a sharper contours of the moving shoes. And here are more visualizations of the model of motion and the interpolation. And after that, we also found that our proposed method can be further improved for perception-oriented interpolation by incorporating an additional learning objective, specifically the LPIPS loss. These enhancements lead to even better perceptual interpolation results, as shown in the table here. And here are the qualitative comparisons presenting the improvements achieved with the addition of LPIPS loss. And now both the code and the pre-trained width of our method has been open sourced. There is also a nice comfy UI version of our methods thanks to Kijai, and feel free to explore them and leave a star if you find it helpful. Yeah, and I think thank you all for your attention, and I'm happy to take any questions if you may have.
Awesome. Yeah, thanks a lot, Zujin, for walking over the presentation. It'd be great if you can also put the link of the GitHub page and some of the reference material in the chat as well, so that people can take a look and follow up. Yeah, is there any question right at this moment for him to answer? Feel free to unmute yourself and ask the question. Yeah, maybe be great if you can quickly go over the use cases of video frame interpolation and like how the benefit of this approach and how yeah, basically the use cases of VFI. That'd be great.
Sorry.
Yeah, the use cases of video frame interpolation.
Oh, okay. So, the video frame interpolation we talk about here is just focused on the traditional video frame interpolation task track, and in this formulation, the video frame interpolation are used to create more slow motion videos or create some special video effects. And normally the input frames here for the traditional video frame interpolation are very narrow in time, in the time axis, and it's about only I think less than 0.1 second for the time interval. So it's just to make the video more smooth and yeah, create a slow motion videos.
I see. So it's about like the smoothness and it capturing more details in more motion.
Yeah.
Within the video frames.
Like temporal super resolution.
Got awesome. So yeah, what's the next step for this work? What's the future direction?
Here as you can see, the future direction can be first of all, you can increase the time interval and perform interpolation at a larger temporal interval, especially in the current era of AIGC. After you generate some AI generated videos from the diffusion models or and for the generated videos, we can perform further interpolation of these videos, make it more smooth. And besides, another point is to maybe introduce some diffusion or generative priors in the interpolation task to make the interpolation more smooth and keep more details. Especially for the small, fast-moving things, current video frame interpolation method still cannot capture the small, fast-moving things, such as the golf stick or the golf ball in high speed.
Yeah, that makes sense. Yeah, super excited about some of this work in order to make the quality of AI generated videos to become much better and more realistic. Right?
Yeah.
Awesome. Well, thanks a lot, Zujin, for finishing your talk. Yeah, feel free to ask more question attendees if you have more in the chat. So with that, Kamran and Amir Hossein, do you guys want to go ahead and start your presentation? Also, Zujin, can you, feel free to share the screen.
Let me share my screen. Okay, so can you see my screen?
Yes, we see it.
Okay. Hi everyone. I am Kamran Janjua, and I'm here with my colleague Amir Hussain, and I will be talking about our work in NeurIPS, which is how to process these streaming videos online. Um, so basically, this work has a application perspective, and which is the video restoration. So I'll quickly talk about what is video restoration, and then just more focus on the method itself. So video restoration refers to the fact that you have a video which is degraded, and it can be degraded through camera noise or motion blur or external weather influence like snow or rain, and now you want to learn a filter or an operation such that this degradation can be reversed, right? So what that means is you get this really clean video back after that. Some of the samples are here. You can see there is snow and haze in the first video, and this sort of filter passes over it and removes the entire thing, and then there is blur and rain in the bottom two. Anyways, so there are three aspects to this work. One is the learning aspect. The other is how to process these videos in a streaming fashion, and then the third just looks at how past knowledge or or the frames that have already been observed that can be used towards this end. So video methods generally they process videos contextually. So what that means is if they're trying to reason about current frame or frame at time step t, they will look at a temporal neighborhood in both the future and the past. So that is but very true of all of the video restoration methods, because there is no differentiation in that, and also some other video understanding methods do that. But real world videos are not captured like this, right? You don't have access to the future frame. You only observe a single frame at a time, and whatever decision making or whatever you want to do, it has to be done using whatever knowledge or whatever observation has been observed by your algorithm. And for all of the real world applications like improving video conferencing or video feeds in self-driving cars, or basically recordings of on action cameras of sports and stuff like that. So we really look at these two major questions in this work. The first is, well, how can we learn from such streaming videos? And the second is that given that we are learning one frame at a time, what is the most effective way to borrow knowledge from the past, right? Because we also want to remember something that might have happened and is now useful. So how can we take both of these into perspective and design our algorithms like that? So the crux of our method is something we call causal history model. It's a sequence to sequence map. What it does is it takes these patches, a sequence of patches at input, and then it gives you the same sequence of patches at output, but does two important functions in between. So consider this frame T, right? Once you can make patches of any granularity. So if you go one by one patch, then that will become a pixel to pixel map. Or if you go 3 by 3 or 5 by 5, then you also have in every frame you also have some surrounding neighborhood for every pixel. Anyway, so given this patch, the first step that CHM does is that it finds and keeps track of the previous top K patches. So for every frame that is being processed, it also has access to this bank of previous frames that it has already seen. So obviously at frame 0, nothing is there, so that history is empty. But as soon as more frames get registered, you have more history bank that you can look into. So we truncate it. That's why it's called truncated, because turns out for video restoration specifically, you don't need to keep frames more than 3 in your history. This is an empirical value, but we will talk about the intuition in a bit. So anyways, so the first step is, as I said, is that for every frame, like current frame that is being processed, you look at, for every patch, you look at the most similar patches in the entire history. So T minus 1, T minus 2, and all the way to T minus 3. And since the frame itself is has some spatial dimension. So we don't look at all of the patches because that might introduce spurious correlations. We just focus on top k patches. So k can be 5 or 10 or whatever number. And just so for every patch in the current frame, just look at top k of these previous patches. And once you have this temporal trajectory across the entire history, what you do is then you figure out, well, which past is most important. So for example, for restoring, because the end goal is restoration, right? So for restoring this patch, for example, this red patch, you figure out, the CHM figures out, well, the patch in t-2 was most important because the rain didn't cover that in t-2, but it is occluded for whatever reason in t-1, right? So then t-2 gets a higher weightage in this, and that information gets propagated. So these two functions is what it is doing. If you look closely, the first step is actually motion compensation, right? It's trying to understand where patch or a pixel is moving throughout this video. And one such method, or the very famous method, is optical flow. You can just compute these dense per pixel motion vectors that tell you for every point, well, where is the where is this pixel in your previous frame or the next frame, whatever two frames that you're passing. So, but in our case, the videos are severely degraded, and optical flow is known to fail in such degradations. The the only solution is that you carry a separate flow network all the time. So once you have a reasonable representation of the frame, a reasonably clean representation of the frame, you compute the optical flow and then do the restoration. But you also have to keep on refining this optical flow network so that it understands that changes are going on. So that just adds to the compute cost of your entire pipeline, right? Because now you have a restoration method and an optical flow algorithm, which is quite heavy in itself uh, if done with deep neural networks. So Turtle had this CHM aspect of our method called Turtle kind of avoids all this. And why it doesn't get affected by the degradation is because the design. So this is the overall design of Turtle on the bottom right corner. It's a unit kind of an architecture. The entire encoder part is historyless. So what that means is for each block of the encoder, no history information is used. Intuitively, because the representation in the encoder stage still have a lot of degraded information in them, right? So it's not properly cleaned. Having history there will just add more compute resources, but give us little to no benefit. A choice we empirically verify. But as you go towards the middle stage or the latent stage and then reconstruct it back, this encoder is acting like a compression algorithm, right? It makes sure that only the most compressed representation is available at the middle stage, such that the decoder is able to perfectly reconstruct the input back. So this is at this point we have these causal history models which are placed as black boxes at each of the stage, and they basically take these one frame input, process it with history, and give you a better representation in the output. And basically you construct your mainframe back. This is the overall structure of the method Turtle. One important thing to highlight is that since it's an encoder decoder, you pass in h cross w, which is basically your spatial dimension of the input, and then at every stage it is downsampled by 2, so it becomes h by 2 at the second stage and h by 4 at the third, and so on. And then it gets upsampled back in the decoder stage. So h by 4 becomes h by 2 and h, and so on and so forth. So this is the compression and the decompression kind of a situation going on. So that's why at this middle point you have 3 times downsampled. Sorry, so it will be h by 8 here, and that is the most compact representation that you can get, and then you use that basically to help reconstruct the frame back, right? Anyways, so one interesting ablation study is CHM necessary. So as we discussed, consider this degraded frame. It is heavily occluded. The patch that is covered in red is nothing is visible. It is a zoomed in version of that same patch, and what you want to do is reconstruct it back to this ground truth, right? So without CHM, as you can see, there is probably something in this window right, which you also want to recover. But without CHM or without having that history, minute details like these, for example, whatever here is gone now, because it is absolutely not, that information is absolutely not available in your current frame. So you have to look at the previous frames and be smart about what is the most important thing, and then Turtle with CHM will help you somehow get that information back. Um, so that's an interesting aspect of why the design of CHM helps with recovering these minor or minute details in the frames. And secondly, as you saw by the design of Turtle, right, it has this recurrent pattern to it because it takes the frame and it only processes a single frame at a time. We also have two different views of Turtle. So what that means is, so given a video of, let's say, 10 frames, right, we divide the video into clips of fixed sizes, so 5 frames at a time, because we are only looking at 3 history frames. You don't need to have the entire video available at the time, in at least in the training. So by doing this, you can parallelize your videos over multiple GPUs. So if you have a video that is 10 frame, you have 2 GPUs, just it's 5 frames on each, and the training is very fast now. You don't have to rely on the full recurrence to kind of only run it on a single GPU. But in inference, you benefit from the design of Turtle. So now that video time steps come rolling in, the more you, of course, the more pass that you give, the better that information will be. And so it, although explicitly it is still only looking at 3 frames, but implicitly it is maintaining whatever it has seen, because the states don't get reset, right? So for example, in the training view, once the new video comes in, the states reset because the previous history doesn't matter anymore for this input. But in the inference, that doesn't happen because it's just one video that is being processed. Um, so it acts as a it benefits from this recurrent structure in its design in inference, but you can have very quick or very fast training over 8 GPUs, or how many ever, given the design of CHM. So because of all of these design elements, one, that you don't need to have expensive operations in the encoder branches. Second, you can process a single frame at a time. You don't need to have 13 or 16 frames to just restore one frame. And the decision of having these two different views of the algorithm helps with almost a linear increase in the memory or the inference time as the resolution increases. So as you see, most of these methods report performance on 256 cross 256, which is just a very small patch of the video, right? But how about processing a 1080p video directly? And then on a consumer 32 GB NVIDIA GPU, these previous methods go out of memory. So only our algorithm or Turtle essentially scales sort of linearly as this resolution increases every time. So is the case in the inference time. Um, and these are some of the selected results of the method. Um, so for example, this is your frame, and you probably can't even see without zooming in, but the foot is what we are looking at, and this foot of this person has this edge that is blurry, right? And now you want to restore this. So these algorithms really are very competent in the sense that they need to restore these minute details, because uh, if the degradation is still present, the end goal doesn't get accomplished, right? Because if your end goal is to get important information from a video that is degraded, and you're not removing it properly, your information isn't available anymore. So that's why you see Turtle will actually preserve the texture of that foot, not have unwanted artifacts, like for example here, or on the tire of this car in the upper pictures. So for example, you see the rim of this car is all over the place, but it's in its correct position in Turtle's output. Similarly, the information point that I was making, the degraded frame here has actually some snow in it, while the sheep also has these white spots on their skin, right? So you don't want to remove that white spot, but you want to remove the snow from it. So that sort of differentiation needs to exist between the two. Um, so for example, if you see there is a white spot on the sheep at this point, and also here, this is a snow particle, not a spot, but this algorithm, the other algorithm, kind of doesn't remove it properly, or considers it as a spot or whatever, but turtle actually preserves the details much better. Same is the case in this another example, where these minor snow flecks on this underside of this banner are actually removed in turtle. As you can see, they're gone, but they're visible here still in the previous method. We also tested turtle on open source videos, so real world videos, sorry, taken from a free videos website. And so this is all real degradations. There is real snow, real rain um, going on here, and that turtle is able to very nicely clean. And about that information thing that I was saying, for example, now you want to know the license plate number of this car in front of you, and it's extremely degraded by the rain. And if it doesn't remove these minute details, you see the output of this, the first two numbers aren't very visible here. But in turtle, you can clearly see that number plate. So that's why these minor details are very important in a video restoration algorithm. And yeah, that's it. Thank you. If you have any questions, I'd be happy to answer them.
Awesome. Yeah, thanks, Kamran, for working over this work. I can see a lot of values, especially for like video editing process, right? When you want to modify certain aspect within the videos, when you use this technique to like make the quality of the video much nicer. Have you thought a lot about like some of the potential use cases that you can apply this work to, like on the application side of things?
Yeah. So one obvious use case is really just cleaning up the video feeds inside driving cars, right? In all weather conditions, you want to clean up whatever weather, whatever snow or rain is falling, so that your lidar camera works well, your optical flow algorithms work fine. So that's one application. The other is we're covering live events or live sporting events, um, and you don't want motion blur or things like that, or unwanted camera noise, for example, sometimes occurs to to affect your videos. Also, in video conferencing, there are compression artifacts because of how these video codecs are written. You have these unwanted compression artifacts that occur in videos, so you want to restore them. But the really the main point of this work is the focus on streaming videos, right? Because you want to do it in real time. You don't want to go offline, run it on a bunch of compute nodes and then get back. You want to do it on real time on your local device or a cloud, but it should be real time, and very quick. So that's really the main focus of turtle.
But and I think like a big emphasis that you walk over is there was a slide about the causal history model when you emphasize the inexpensive compute part during inferencing time, right? Maybe the next slide, actually.
This one.
Yeah, they said in inference time.
Yeah. So the point is that there are two different ways of how you can operate this causal history model. The one is the training way, the training phase, which allows you to parallelize your videos frames so that it can train quickly. You don't have to rely on the entire video to complete, especially when the video is very long. And but in inference you want to rely on the recurrence, because you don't have multiple GPUs in your inference, right? It's just one chip that your algorithm is running on. Second, you want to benefit from that. Obviously, the longer your temporal trajectory is, the better information you are getting, right? So you want to benefit from that as well. So in inference it just rolls out over time steps. You don't really have to reset everything, or have that parallel structure in inference. So that's a speed up. um, you one interesting future aspect will be, I think it's important that we discuss that, is that right now we've only really scaled it to 1080p because it doesn't use some of the modern quantization algorithms or things like that actually help with even speeding up the algorithm. So I think one thing that we're interested in is how to scale 1080p to 4K at least at 30 fps so that it can process these videos really quick.
Yeah, for sure. So and it sounds like a big chunk of your focus on your research is on the online learning domain, right?
Yes.
Um, I'm just curious. Like, I haven't paid a lot of attention into that research direction. Was there any like novel techniques or approach, especially around optimization, to like accelerate online learning?
So my main focus is basically how to learn from the streaming data, right, or online data, where the data is arriving in samples, and this kind of limits, because most of these algorithms are designed to assuming batch access to data, and so your speedups are like that as well. So for example, if you have a network that is trained and you do post training quantization, how that would affect if you don't have batches anymore and you just learning on a sample, that is something that's not explored. So we try to design algorithms, especially when in two different phases. So for example, you already have some amount of offline data, you want to benefit from that, but then also when you move to online setting, you want to learn this offline data, such as it quickly helps with learning online, right? If you see what I mean. So you benefit from whatever data is available because there's a lot of data available, but you also quickly adapt to online setting so that you don't have to see a lot more online samples before your algorithm starts to give out reasonable outputs. So that is also a very interesting
Yep.
aspect of the direction.
And there's one question on the chat that is pretty detailed. Do you mind answering it?
Okay.
Just look at the chat. You can stop sharing the screen, by the way, so you don't have to juggle between different screens.
Okay. So should I stop sharing? Is that what you're saying?
Yeah.
Okay.
Just stop sharing, and then just so you can look at the chat.
Okay, so the question is, for scaling, have you thought about parallelized interpolated frames to say output 4K at 15 FPS while interpolating the other 15 frames in mostly parallel so that you get realistic 30 FPS? And 30 FPS is sufficient to capture the key aspects of the video. The way you can do online processing too, and the compute for 4K, okay, so I'm putting 4K 30 FPS online with little delay, as long as you have the compute for it. So we don't do interpolation, but what I'm gathering from your question is that you're saying half of the things.
Yeah, if you want to unmute, just ask.
So are you going to ask? Okay. So we don't do interpolation. We just do restoration, and I think that what you're saying is that you can at 15 fps you can process 4K, but you output 4K at 30 fps with little delay because you are storing more frames as you go roll over that. So that yes, obviously that's one way to do it. For example, in online time series prediction, when you're predicting 100 steps into the future, only at the only up till the 100th point you're actually looking at the future frames, right? So for example, you are at time step 0, you want to predict time step 100, that's 100 step jump, and then 1, now you have the previous as well. So 2 and 3, you have more data that accumulates, and at 100th one, if you want to predict the next 100, you already have 100 samples with you. So yeah, online algorithms are designed, if you want to do things like that. That is a decent idea, yes. But we haven't tried interpolation or actually running at 4K 60 FPS, because our application is even smaller than cloud compute. It's just on your phone, so you don't run these huge networks anyway. We in the academic setting, since the methods that you're competing with have a set design in terms of the Gmax that are available to them, right, or the parameters that are available to them. So you have to scale your algorithm such that so that they match. But when you deploy them, it's a different story there.
Oh, we couldn't hear you, Pranay. I don't think we hear you.
Can you hear me now?
Yep. Now,
Yes.
now it's cool.
Oh, I apologize. So yeah, I was just asking if you had considered it, because you mentioned specifically 4K 30 FPS, so I gave the example. Towards the end is something that you would perhaps like to go towards. And I know that's like that's very compute intensive, and so aside from the other things like quantization, whatnot, and this is assuming that the task is capturable within those frames, so it's not like some like needle in a haystack or some well, I mean, I guess it could be that, but it's not like some high speed thing you need a high frame rate capture, obviously. But yeah, I'm wondering also if like with those frames, and you could also test this on some very small images or videos rather than large ones, so you need less compute. It was just an idea, and how well that would do because of how much are things really changing frame by frame, and then even with the interpolation, it's like, could you focus certain patches on what the optical flow between the frames are actually showing, and then only have to really process relatively little. So anyways, that's a lot, and I don't want to take up too much time, and it's more so just like ideation, and if you want to discuss offline, I'd be happy to also.
So can you hear me still?
Mhm.
Yeah. So this reminds me of a method from NVIDIA, I think a couple of years back, where if you have really choppy video input, right? So they only send, instead of sending the entire frame in packets, they only send what's changed, because your background isn't changing. The expressions are the only important thing that is changing in a video conference.
Mhm.
So yeah, neat idea. Worth looking into.
Nice work.
So, all right. Thanks, Kamran. Really appreciate you walking over it. Super exciting work. And yeah, I know streaming video is something that, we internally at 12 Labs looking at it as well. So always good love to stay updated, right, on what's the research side of things, how to handle this complex, especially on the processing side of things, this complex online pipeline coming in. Yeah. So yeah, with that, yeah, let's have the final speaker to jump in. So yeah, Mingfei, I think you're in the call right now. Please go ahead, share the screen, and start the presentation.
Okay, sure. Yes, can you see my screen?
Yep, what is it?
Okay, I'll make it quick. So today I will share our benchmark for video understanding as for multi-shot videos. So let's start. So for the first one, let's watch this video clip. It's a short video clip. You can see that is this video is not just one thing, and I create a different shorts with different content and different video clips. You can see it actually, for this video, contains several distinct shots, and each capturing specific visual information. And yes, and let's quickly summarize each shot here. And we can see in the first shot, a man like seems cutting something and have him hurted. And the second shot, we can see a close-up reviews. What is somebody is cropping something. And for the next shot, we can see a woman is praise something with the thumb up, and finally we can see clearly a promoted product. And so this is let's what we are talking about, the multi-shot video. So for a single video clip, it is for a holistic topic with some promotion topic, for example, and it contains multiple shots. So we think that real world videos are actually stories. And for stories, it definitely span multiple scenes, and with each one contributing crucially to understanding. And also, for the sample video I show, I think it clearly demonstrates that why multi-shot videos understanding matters. So to understand this video, and we do not, I mean, it is impossible for us to see only single video shot for see only a few frames to understand what is going on, what is the event progression is, what is the short transition is for this multi-shot video. So in order to promote the research and a better understanding of such multi-shot video, actually we introduced a data set actually with a large-scale human annotation called a short story. So for this data set, we carefully annotate different aspects of a multi-shot video from the multimodal perspective. So first one is the single shot video caption. For this annotation, and we only care about content in single shot. And say that we have 4 shots here, and we annotate different content in different shots and detail, and then we annotate the narration captions, basically about the audio content, which build a connection between visual and audio content. And then we have this multi-shot video summary. For this summary, it contains the contents from different shots with detailed descriptions, the essential, the event transitions, event progressions, and the short transitions, with finally a conclusion on how the videos look like, what is topic, what is content about, to better promoting the understanding. And finally, we propose this multi-shot video QA. For this QA, it spans across different question types to do better understanding from the perspective like temporal order of different actions, different event, or from a holistic view to like what is the video is all about. And also more important is about the audio content. I mean, in this benchmark, the audio content is related to its vision content. And we do this such annotation like to query about what is going on in the audio or how it is related with visual content. So this is the different annotation we provide in this benchmark. And here is so here is a statistic of our short story. Overall speaking, we have over nearly 200,000 single shot video captions. And we have nearly half of the narration captions because not all the single shots have some the audio content to be annotated to be visually related to the videos. And for this part, we annotated both of the training data and the validation and testing data. And we additionally provide 11,000 multi-shot video constraint answering pairs for evaluation only for validation and for testing. So in detail, let's get an overall view of our data. Is so for our multi-shot video, generally it has 3 to 5 shots, with 4 shots being the most common. And also for the typical short durations, here is it is short. It's much more like a traditional video captioning task, video captioning data, and predominantly around 1 to 4 seconds. But we provide quite detailed short video captions with the words around typically 20 to 40 words, ensuring we provide sufficiently detailed description of each short video elements. And we also have this the narration captions, which the content is related, and then the annotation is closely related to the visual content, and which typically have 10 to 20 words. And this is our detailed video summary statistics with the length ranging from 150 to 250 words. So this is kind of a rich and coherent narratives with quite detailed content. And as our video is sourced from HD Villa, so it inherited its video categories spanning all these different categories and with predominantly on the entertainment, news, and politics and sports. So this is all about our video captions and the video summaries. And additional, we have all these video question answering pairs for validation. So we typically annotate 3 different types, like the temporal related, audio related, and the holistic understanding related. And for different question types, for different questions, it may have 2 or more question types. So this is how our video question answering pairs is looking like from a statistic view. And so this is kind of overview of what our data set is providing. And the one thing I want to lay stress is our annotation quality. So this is both for training and for validation, for testing data. Human is fully involved and do the corrections on the text annotation. So for video summaries, it is initially generated from GPT-4, which integrates all those video single short captions and narrations. And of course, and these short captions is also obtained through the extensive human annotation and corrections. So finally, the human annotators actually carefully read all those GPT-4 generated summaries and do the manual corrections on those factual inaccuracies and misinterpretations and all other mistakes that to ensure that such annotation accurately reflect the video content. And so next step is about our question answering pairs. Of course, and is human involved. The thing is how we obtain these diversified and high quality questions and answerings. First, we use GPT-4 again to get a large pool of initial question answers. And we ask annotators to do manual selection of those questions. The first one is it needs to be closely related to videos, and it needs to be can only be answered by watching videos. So we do this manual selection of the questions, and then we ask them to do question filter out. Like you can only keep those questions fall into our predefined 3 question types. Finally, after having all those questions, and we have initial drafted answers from GPT-4, and we ask people and the annotators to do manual correction again to ensure the questions and the answerings are paired perfectly and related to our video content. So this is all about our manual annotation pipeline to ensure that all the things is of a high quality. And followingly is our simple baseline is just a simple baseline for the multi-shot video understanding. So you can see here the structure is quite simple and similar to existing works. This is Q-format based multimodal models. So we arrange the video by its shorts. Simply put, it's just we enable the short structure in this video. Like we have this video, it has 4 shorts. We explicitly mention this in the prompt, and we arrange the visual tokens of the different shorts with the short orders index here to let the language model see, okay, so here we have 4 shorts, and what is the first short with the second short, and we can flexibly provide the ASR content here and ask the model to do a description. So it is generally is a summarization model, and we train the model with only either captioning data, either summarization data to do this detailed text-based understanding of the videos. So this is our baseline looks like. So through this baseline design, we actually find some and provide some insight into this multi-short video understanding and processing. So here is kind of 3 tables. So put it quickly. So first one is for the video short captioning. And one insight here is as we can see the lines here, either based on the video chat tool or based on the mini GPT-4. So the S means the subtitles. The V means the visual, like the tokens only. So with the subtitle involved, we can see improvement here, consistently improvement here for the single shot captioning. And for the second table here is actually the multi-shot video summarization task. Two insights here is the first one is similar to the single shot captioning. Involvement of the subtitle improves the performance. And the second side is that we can see here is a mini GPT-4 based model. One is holistic model. Holistic model is similar to all the other video models. We uniformly sample frames from the video without the short structure mentioned in the training. And the short here is we explicitly mention the short structures in the model training. So we can see with such short structure involved, we can see the improvement here, and we by manually visually verify that the generated video summaries can actually better capture the event progression and also the short transitions. So this is our insight for this multi-shot video summarization here. And moreover, and for the third table is all about the question answering. Oh, sorry for this one. So for the question answering. So for question answering, we have a kind of a different experiment setup. As I have mentioned, our training only involve all those captioning and all those summarization. So it is from some aspect, it lacks the ability to instruction following question answering. But we find out that through a text-based approach, like we use the Vicuna 7 billion version-based all those two models to train our sum shot model, and we do the question answering with only text. The text here means the video summaries. The video summaries generated by our models. And even with only text-based, only text-based question answering using the same LM, let's say the Vicuna 7 billion version, we could achieve some advanced performance here on our test and validation sets for our question answering task. So continue with the question answering task here. Actually, we here have the zero shot video question answering performance. As I mentioned, the model is only trained on our videos from HD Villa with our summarization annotations. So it is a summarization model. So in order to do the MS or VTT QA or in-net QA, we again generated the summaries. And why we call it zero shot, of course, our model doesn't see this kind of videos either. So in the previous era, we call in-net is a long video. Of course, currently it's not, but in the distribution is most of the videos looking like a single shot video with a kind of long duration. So kind of different domain to our training video. So we call it a zero shot VQA. We can, let's say we can still have a good performance. Good performance compared to the concurrent models like the Video Lava or Video Chat 2, because I think one thing to mention is we only use the generated text summaries. So this is all about our zero shot QA experience here. So in conclusion, actually, we provide a human-annotated high-quality data set, including training, validation, and testing for summarization, for captioning, and also we provide a question answering benchmark on the perspective multi-shot videos. So this what we provide in this benchmark, and then we provide some insight here. Okay, so that's my content today, and thank you. And if there's any questions.
Awesome. Yeah, thanks, Mingfei. It's a very exciting work. We can spend like 5 more minutes to go over a couple of questions that we have. Well, first of all, I just want to say that this is like super relevant to the work we're doing at 12 Labs. When we benchmark our model Pegasus, we did it against like Video Llama, ChatGPT, and all the benchmark that you shown in the table. So perhaps we can like consider short to story as another benchmark that we can evaluate a model on. Yeah, so just want to highlight that point. So there's a question by Michael in the chat. Do you mind answering it? The first, the most recent one.
Most recent, yeah. Are you doing short detection? Is for plus use? So, So the question is whether I'm defining different things or different shots, and am I doing shot detection, right? So the answer is yes. We do do shot detection, kind of like a pre-processing. So before doing all the things, if we want to include the shot structure into the model training, we need to have the shot detection results. The answer is yes. But if you only want to do some validation or testing our multi-shot video benchmarks without these short structures, I think it's good and free to discard all those short structures to do your model training or testing. But in our annotation and our baseline, the answer is yes, we do short detection as pre-processing. And the method is CNN-based called Transnet V2, the model we are using for shot detection. Okay, that's my answer. And if I did answer a question.
Yeah. And then I think the most interesting question about taking EDL, defining the short frames accurately as an input. I'm not sure, because I feel like this is a research part. Yeah, Mingfei come from a research background, so I'm not sure he's familiar with EDL. So that's my guess. You know, for
I'm also not actually. I'm also not familiar with EDL. I'm sorry.
yeah. And then you mind answering the question above it about the basketball thing?
Yeah. A list of time code for each short and stop and take EDL defining the short frame. So I'm sorry, I will continue on Michael's question. Yes, the answer is yes. So actually, you can take, let's see the baseline structure here. Every information about the short structures, yeah, you can input into the prompt for training. But actually, as I remember, we have an initial trial on this thing. It's not good for summarization. It doesn't bring improvement on performance with the time stamps involved in the training approach. So that's my answer. Yes, you can, but we don't see improvement.
Great.
Okay, back to basketball. I'm sorry, I'm taking quite long to read this context.
Yep.
Okay. So I don't know if I understand the question correctly. It's like you are doing something on the basketball game video analysis, right? So the thing is you want to know, so one is from Sam, one is from mine. How can this understanding help with so learn the matrix like shooting sectors? Yes. So actually, this reminded me of a previous research I have done. It's called group activity recognition. So I think the similarity here is for a game for like basketball or for volleyball. The thing is the whole thing is cut into several different shots. I think it's similar, or like for your basketball thing, when you're shooting, when you do some interaction, you can call it as a shot. If you call it shot, you need to define. You need to define it as a shot if you define it as action or event. So I think the multi-shot techniques can help with this. But first of all, you need to well define what is your structure is, what your shot is, what your event is. So that's the first thing. Then the second thing is like you called how we can the multi-shot video thing can help with this like matrix like accuracy and efficiency. I think if it is doing some overall or holistic analysis, multi-shot video can surely help. But if you are doing some like matrix thing, I think it mainly depends on how you define what I say the shot or the actions of the players on the court. So that's
Yeah.
my answer. Hope it helps.
Yep. I think that makes sense. All right. Well, I know we a couple minutes over time, but yeah, thanks again, Mingfei, for working over your work. Super relevant, and I know you're on Discord as well. So if there's more question from attendees, you just ask him on Discord. And
Yeah,
you
sure.
know, yep. Once again, thanks all the speakers for presenting today. Appreciate your. I think all the topics that we discussed today are pretty interesting, right? So frame interpolation, multi-shot video understanding, video restoration, they are somewhat relevant to kind of the work that we're doing at 12 Labs. So I personally find this being very educational to just learn about these different techniques to, help us understand from an academic point of view how we can improve our processing workload, etc. So yeah, I appreciate the time that you will take to prepare the materials. The recording of this session should be available on YouTube by early next week. So, probably Monday, Tuesday. So be sure to share the recording with the speakers so that they can have the material for sharing. And yeah, thanks to attendees for spending the time on a Friday to attending webinars. We'll run this session on a weekly basis. So yeah, if you find this content valuable, please come by next week for more presentation. So thanks everyone. And hope you all have a great rest of your weekend. Bye-bye.
Bye-bye. Thank you, guys.